Hello and welcome to ESMARConf2022 and this session on network meta-analysis. As always, this session is being live streamed to YouTube and the individual presentations have been pre-recorded and published there as well. Subtitles have been verified and can be auto-translated for those individual talks, and automatic subtitles will be available shortly for this live stream. If you have any questions for our presenters, you can ask them via the presenter's individual tweet from the @ESHackathon Twitter account. See them on our feed. Presenters might have time after their talks to answer some of those questions or at the end of the session if time allows. And we'll endeavour to answer all the questions soon after the event. We'd like to draw your attention to our code of conduct, which is available on the ESMARConf website at esmarconf.github.io. So our first speaker is Silvia Metelli, who is a postdoctoral fellow at the University of Paris. Silvia, over to you.
Hello, everyone. In this talk, I will present NMAstudio, which is a new online and interactive web application to produce and visualize results from network meta-analysis. This is all joint work with Anna Haimani, also from the University of Paris. So the main reason behind NMAstudio is that we wanted to provide a tool that could not only enhance, but also facilitate the interpretation of the main findings from a network meta-analysis. We know that network meta-analysis, by integrating direct evidence with what is called indirect evidence, can simultaneously compare many treatments. And for this, typically there is a very large number of results and outputs being produced. So visualization can be challenging, especially when we have large networks with many treatments. Also, more recently, it seems that we are moving towards the context of living evidence, so with data collected weekly or monthly. So we need new software to keep up with this fast production of evidence. However, existing software in the field so far are not fully interactive in the same way we hope NMAstudio can be. So a bit more specifically, NMAstudio is a Python application that connects to R to produce the NMA results using the library netmeta. Then those results are imported back in Python where the app is built. In NMAstudio, users upload their data and interact directly with a customizable network plot by clicking on different nodes, so the treatments, or different edges, so the comparisons. And based on their selection, different outputs will be displayed. So NMAstudio will follow all of the key steps which are typically performed in any published NMA, starting from the very first assumption of and fundamental assumption of transitivity. And then once this is met, typically a large part is dedicated to the reporting of a summary of the treatment effects in the form of forest plots or league tables. Then, importantly, we need to assess whether consistency holds in the network. So if there is statistical agreement between direct and indirect evidence, and also to assess for the presence of small study effects, which is a phenomenon related to the problem of publication bias. Finally, a ranking of treatments is usually provided. So NMAstudio will assist the user in each of these steps, and we will see this how with a demonstration. So our data come from a recently updated systematic review about chronic plaque psoriasis, which comprehends 158 RCTs and compares 20 different drugs. There are two primary outcomes that will be analyzed, one for efficacy and one for safety. In this case, both outcomes are binary and risk ratios will be used. So we can just have a look at the app. Okay, so this is the main homepage of NMAstudio, and first thing you will need to upload your own data from here, selecting your data file, for example, and data format or type of outcome. Here I've already uploaded the data, and this is permanently loaded, actually, this example into the app. But once the data process is completed, your network plot will appear here on the left. This is a completely interactive object, so you can move it around, zoom in or out, or also drag every item. Also, there are additional settings here, starting from the layout. So you can change layout from a list, you can change edge sides or node sides, for example, and also a few options about coloring the nodes, for example, by risk of bias that you will have in your data, or by class of treatment, if you have that, and also just choosing your desired color, and same for the edges. Then you can download the plot from here or look at an expanded version from here. Still, in terms of network visualization, we added an option to look at the evolution of the network over time with the slider here on the right. So, for example, if we click on the very first data available for this data in 1963, we can have a look at the first trial, and then we move on over time, and we can see how evidence is added. And also you will see that the data table is filtered in real time accordingly. Also, in terms of data filtering, you can filter your data set just by clicking on a few comparisons, so edges in the network or a few nodes, and the data table will be filtered accordingly again. You can also have a look at the expanded table and export the data in CSV. Okay, so now we are ready to start all of these key steps of the NMA that I was referring to before, starting from transitivity. So to check transitivity, we need to check whether the distributions of the potential effect modifiers that you have in your data set are similarly distributed across comparisons. You can choose your effect modifier here. For example, we have a look at age, which is typically provided, and the corresponding plot will appear here. Also, these axis labels, and this is true for all the subsequent plots, are editable. So, for example, here you can just choose your label. And also, if you want to highlight a few comparisons of interest, you just have to click on the corresponding edge in the plot. Moving on, we have the summary of the effects. So starting from forest plots, here we have three options: an NMA forest plot, the typical pairwise forest plot, and the bidimensional forest plot, in case, of course, two outcomes are given. So starting from the first one, here, of course, we will need to choose a reference treatment, and we do so just by clicking on a node on the network. We can have a look at the plot. Also, you will have to choose the correct direction of the outcome to interpret the plot correctly. And we can also have a look at the plot for the second outcome. In this case, the network plot will be automatically updated for outcome 2. Then for the pairwise forest plot, of course, in this case, we will have to choose a comparison. And you can resize a little bit the objects. And also, again, you can have a look at the plot here for outcome 1 or 2, and you can save it. All the plots will, you can save it from here. Then moving on again, we have the bidimensional forest plot. So you will have the forest plots for outcome 1 on the x-axis and for outcome 2 on the y-axis. Again, we just choose a reference treatment. The forest plot will appear here. And in this case, you will have to pick the correct region of the plot to interpret the results correctly based on the direction of the outcome. Also, you can click on the legend to remove sequentially a few treatments if that's needed. Then again, we have the part dedicated to the league table. So league tables report all of the possible treatment effects between any possible pair of treatments in the network. So they tend, of course, to be very large. And here you can see that you can scroll the table. We also allow for two different options of coloring the table. First, default option by risk of bias. In the direct comparisons, you will have the average risk of bias, but also coloring by report from Cinema assessment. So Cinema is a software that reports an overall rating in the confidence of the evidence, which is graded as very low confidence, moderate, or high in each comparison. So what you will have to do is to upload the results from that you get from Cinema for both outcomes, of course, and then have a look at the corresponding coloring here. On the lower part of the triangle, we have results from outcome 1, and on the upper for outcome 2. Also, you can have a look at the expanded table here, and you can export it, maintaining coloring and formatting. But what is important here is that, as we said, league tables tend to be very large, so you might want to have a look just at a subset of nodes which are more of interest. So you can do so just by clicking sequentially on a few nodes, and you see that the filter table will appear here. Then, moving on, we have other checks. So starting from consistency. In this case, in NMAstudio, we allow for 2 different options, a global test for inconsistency, which is the design by treatment interaction model, and a local test for inconsistency, which is the node splitting approach. You will see that you have all of your results here in the tables for the node splitting, for all of the different direct comparisons. You can scroll down and you can see that suspicious p-values are flagged in red or yellow. Also here you can filter the table, just picking a few comparisons of interest. Then we have to assess for the presence of the small study effects, and we do so using the typical funnel plots, in this case, comparison adjusted funnel plots. Here also we have to pick a reference treatment. So again, we just do so clicking on the network, and the corresponding plot will appear here for outcome 1 or outcome 2. Then finally, we said we have the ranking of the treatments. In NMAstudio, we allow for 2 different plots, heat map reporting p-scores for both outcome or for one outcome only, and a scatter plot of the p-scores. So p-scores are the frequentist analog of the more common sucra values. And what is important here is that you will have to choose the correct direction of the outcome. So for example, outcome 2 for us is harmful. So we change this here, and we will have our heat map here with treatment sorted from best to worst. Then we have our scatter plots reporting p-scores for outcome 1 on the x-axis and for outcome 2 on the y-axis. Again, you choose the correct direction, and you will have, of course, on the upper right part of the plot, treatments that appear to be the best in both outcomes. But what is important here is that you can use the network plot to assist in the interpretation of these results. For example, if we just look at some more details, we can see that the best treatment is actually a treatment which is, at low risk of bias, but also not very well connected. There is only one trial assessing this treatment. So it is always important to use the network to assist in the interpretation of the findings. So this is pretty much it for functionalities of the app. We also have a documentation page and a news page. So just to conclude, we have seen how NMAstudio is a fully interactive and flexible application, and that it can simplify the full NMA process while also assisting in the interpretation of findings. However, as all softwares, it comes with many benefits, but also with many risks. So we always really highly recommend to use NMAstudio following advice from an experienced statistician. There are many features that we would like to add to NMAstudio. Just to name a few here, we would like to add more options to customize our network plot, and also a more robust system of alerts or warnings, for example, printing the errors from the R console directly. For sure, we will add an option for performing Bayesian NMAs, and also we are looking into ways to provide each user with a permanent link to their project. NMAstudio is also accompanied by a Python package, which is currently under development, but that will be available soon. Of course, this is not an exhaustive list, so we can add more. And if you have any suggestions or ideas, that will be more than welcome. So you can get in touch with me at this email address here if you want to discuss more. Thank you very much, everyone.
Wow, such a useful software for NMA users. Thank you, Silvia, and we look forward to seeing you again for Q&A at the end. So if you have any questions for Silvia or any of the other presenters, please do post them on YouTube or on the tweet thread under her name. I'm delighted to introduce our next speaker, who is Virginia Chiocchia, who is a doctoral researcher at the University of Bern. Virginia, over to you.
Thank you, Ciara. I hope you can all see my screen and can hear me as well.
We can.
Okay, so thanks for joining. My name is Virginia, and today I will present the ROPMAN app. So the ROPMAN is the first tool to assess the risk of bias due to missing evidence in network meta-analysis. And the tool and underpinning framework has been published in BMC Medicine. In a few words, the framework works in a way so that it evaluates the risk of bias in network meta-analysis first by evaluating the risk of bias in each pairwise comparison that can be made between the intervention in the network, considering both within study and across study risk of bias assessment. Then the risk of bias in each of the pairwise comparison is combined with the contribution that each direct comparison makes to the network estimate, together with any presence of small study effects and any bias in the unobserved comparison, so that we reach a final level of risk of bias in the network estimates, and we give a level of either low risk, some concern, or high risk of bias. But due to time reason, I'm not going to go into the details of the framework, but I want to show you what we have developed as the app that semi-automates some of the assessment. This is because due to the nature of network meta-analysis, such assessments obviously are more labor intensive than a standard pairwise meta-analysis. So this is the rationale for developing an app that semi-automates some of it. So the app is already available, and first I'm gonna just show you the data, then an example of network, the data that I'm gonna use to demonstrate the app. It's a network of antidepressants from head-to-head studies, and the network graph is shown here. So the first thing the user is prompted to do is obviously load the data. It has to be loaded as a CSV file, and then the user can view the data here. It's also important, as you can see, there are some studies that do not have the outcome of interest. They have blank cells, so not missing values here. And this is important because these studies can be informative about the selective outcome reporting bias, which will be assessed in the app, in the tool. So the next step is to move to the data analysis tab, where the user has to select the parameters for the analysis that are run by the app, are required by the tool to do some of the evaluations, some of the assessments. So, and then you can start the analysis by pressing the button. Depending on the size of the network, obviously the analysis can take a few moments, a few minutes. And for this reason, I've already run the analysis before. And this is essentially what you will get once the analysis is completed. So first of all, you will get a data summary with a network graph and various other characteristics of the network, interventions and comparison, as well as the outputs from both frequentist and Bayesian network meta-analyses, which are run respectively with the NetMeta and the BaxNet package, as well as also the output for the Bayesian network meta-regression. But I will move straight to the main output of the tool and of the app, which are the tables where to record the assessments. So first, we will have the pairwise comparison tables. Here, all the possible pairwise comparisons are automatically grouped according to whether they have data for the outcome of interest, as shown here in Group A, or only data for other outcomes. As we can see here in Group B, we have 2, or whether they've been, the comparison are totally unobserved, so there actually is no data, no study identified for those comparisons. Another thing that the app does automatically is calculating the total sample size and the total number of studies in each comparison. So this is important for the first assessment, for the within study assessment of bias, which is commonly known as selective outcome reporting bias. So specifically here, this assessment is only done for those comparisons for which we have found extra studies that do not report the outcome of interest, but only report other outcomes. Because we need to assess whether the reason that the studies are not reporting the outcome are due to the results found in those studies. So if the outcome was not reported, the outcome of interest was not reported because we think that the authors didn't like the magnitude, the direction of the results, then that it's informative of selective outcome reporting bias. But the users also need to take into account the effect that this will have on the total synthesized results. So that's why in this case, the sample size is important. For example, here we see in comparison 6, there are 2 extra studies, and we have judged them as suspected bias favoring fluoxetine because we think that the 2 extra studies did not report the outcome for the reason that I just mentioned, because of the magnitude of the result, the direction of the results. And we think that's enough to affect the synthesized result. But you can also see in comparison 9, there are 5 extra studies that either we thought that the reason that they did not report the outcome was related to the magnitude to direction of the results, or the extra sample size was not enough to affect the already quite large sample size. That's why we had judged it as no bias detected. So obviously, as I said, this assessment is only done for the comparison for which we found extra studies. Also for those in Group B, obviously cannot be done for the unobserved comparison. But the next assessment, the across-study assessment of bias, which is also known as publication bias, can be done for all of the pairwise comparison. This assessment is done primarily considering qualitative techniques, qualitative considerations, such as whether the reviewers were able to get data from gray literature, or whether there is well-known publication bias for a comparison or that field. Additionally, if there are comparisons with at least 10 studies, then some quantitative consideration can also be taken into account, such as tests for small study effects and funnel plots, which are also calculated by the app, as you can see here, the data analysis tab. But as I said, these are only in addition to the qualitative consideration. Once again, the user has to then select no bias or suspected bias with the relative direction for each of the comparison. Then to arrive to the overall bias judgment, the user can simply press this button here, which it says that it applies an algorithm. The algorithm is actually really simple. It just checks whether there is in either of the previous assessment a suspected bias. In that case, then it's suspected bias, also in the overall judgment. Once these level for the overall bias are done, then we can move on to the main output of interest of the tool, which is the Rodman table, where we record the risk of bias assessment for each of the network estimates. Once again, the network estimates are automatically grouped into mixed only direct or indirect only, depending again on the availability of the data. And the first thing here is the evaluation of the contribution coming from the evidence. Specifically, the app calculates automatically the contribution matrix, which you can see here, and you can also download, which shows how much each of the direct comparison contributes to each of the network estimates. So this contribution is used then in the Rotman table together with the previous overall bias assessment to see how the contribution of evidence with suspected bias it's split in the sense of like in which direction it's going. And again, this is done automatically, as you see in the first two columns. What the user has to do is evaluating this contribution in this direction. So here the user has to make some sort of like subjective decision. For example, here we decided that if there was at least a difference of 15, then that will be enough to count as substantial contribution. I'll give you some example. You can see here that if there is at least 15% going in a specific direction, then we will go for substantial contribution from bias favoring a specific treatment. If it's not 15%, then it's no substantial contribution from bias. But there are also cases, like for example, let me find some, here, duloxetine versus fluvoxamine, versus milnacipran, it's 30 and 36. So the difference is less than 15. And that's why we selected substantial contribution from bias balanced. So the next assessment is a bias assessment for indirect evidence. This is because the unobserved comparison has obviously no weight in the previous part, in the part of the contribution from the evidence. But we had judged the unobserved comparisons in the previous stage, in the previous table, for risk of bias. And this can lead to bias if the reason that the studies are missing is related to the results found in such studies. So what the app does here is essentially just considering the previous assessment for the unobserved comparison, so the overall judgment that we had in the previous table, and copy it in this column here. As you can see, it's grayed out for the direct or mixed estimates. This is because we have already, there's no need to do that for the mixed estimates, since the unobserved comparison, we have already counted the direct comparison in the contribution assessment. So we only need to consider them for the indirect estimates. And that's what the app does. It's just copying the previous assessment in this column. The final assessment is the evaluating whether there's any evidence of small study effects. And again, automatically, the app reports the unadjusted estimates from Bayesian network meta-analysis, as well as the adjusted estimate from the network meta-regression. They use the smallest observed variance as a covariate. And what the user has to do is check the point estimate as well as the overlap of the credible intervals to see whether there's any evidence of small study effects for the network estimates. So I can tell you, without going through all the 153 estimates, that there was no evidence of small study effects because there was a good overlap between the confident credible intervals, and the point estimates were not that different. So we can also just set them all as no evidence by pressing this button here. And finally, we can then find our overall risk of bias level. And we can easily do that by pressing this button that applies the algorithm that we propose in our paper. I don't have time to go through the algorithm, but what I want to say is that if the user does not agree with our rules, our algorithm rules, so we want to use stricter rules or less strict, then you can also change this manually. As you can see here, the app allows you to change it. It will just show you with a yellow warning in this sense. But also these manual changes can also be done in the previous table. And finally, both tables can be downloaded, which can be useful for reports, for example, as you see here. And we are at the end of our demonstration. So I will just show here the link for the app, which is, as I said, already available to use, the paper. And I also want to mention that we are planning to, we are drafting a paper which is going to serve more as a manual for the app. So it's going to be more technical paper. There's also going to be a live webinar organized by the Cochrane team for the Cochrane training, and it's going to be on the 5th of May. So it's going to be obviously longer than 15 minutes. So there's going to be more details about the assessment and also show all the functionality of the app. I also want to mention that the RobMen is now integrated in the NMA framework and web application, specifically in the reporting bias domain, where the user is prompted to upload the RobMen table. I also want to thank the two people that really helped me with the development and improvement of the app, Clareece, Papa Costantino, and Alex Holloway. And finally, I'm happy to take any question at the end of the session, or otherwise you can contact me on Twitter or by email for questions or feedback, which is always appreciated. Thank you very much.
Thank you very much, Virginia, for your great timekeeping while presenting live, but especially for showing us how to use this tool to critically appraise the studies across this evidence base. So our third speaker in this session is Clareece Nevill, who is a research associate at the University of Leicester. Clareece, over to you.
Cheers. Great. So hi, everybody. I'm Clareece Nevill, and I work as part of the Complex Review Support Unit based at the University of Leicester in the UK. And today I'll be sharing my work around developing a novel, multifaceted graphical visualization for treatment ranking within an interactive network meta-analysis web application. So treatment ranking within network meta-analysis is a really powerful tool, but the results can often be misinterpreted or used or presented inappropriately. As a consequence, we as a team wanted to improve the ranking outputs within our NMA web app, MetaInsight. Therefore, we had two aims. Firstly, ascertain the current methods and visualizations for treatment ranking within NMA, and secondly, develop a novel graphical visualization for MetaInsight. To make sure we're all starting at the same place, I'm going to quickly introduce NMAs. So firstly, the standard method for gathering evidence systematically whilst also appraising and synthesizing the evidence is called a systematic review. To then obtain a quantitative pooled estimate of the outcome of interest in your review, one can run a meta-analysis to quantitatively compare healthcare interventions or treatments. The next step is to simultaneously compare multiple treatments, which can be done with a network meta-analysis. This is done by forming a network of studies and treatments, and then the NMA uses both direct and indirect information to estimate relative treatment effects. And it is through NMAs that treatments can then be ranked. Our first step was conducting a targeted review of the literature since January 2011, looking at papers that introduced, discussed, or compared ranking methodologies or visualizations. This gave us in total 29 academic papers and articles. Within that 29, there were 2 articles that were particularly useful. As part of their paper, Veroniki and authors produced a wonderfully concise summary of common ranking statistics and their primary characteristics. And the paper by Kosmeier and authors is a brilliant detailed record of graphical visualizations currently used within the field of evidence synthesis. So from these articles, what did we learn about treatment ranking statistics and which ones are important? I'm going to bring forward 4 key points I found. Firstly, most ranking statistics are based on Bayesian methods, where multiple simulations are run, thus giving rank probabilities based on the rank distribution outputted from these simulations. Secondly, a popular option that appeared was the surface under the cumulative ranking curve, aka the SUCRA, and this does what it says on the tin. It gives a single value but incorporates the entire ranking distribution, but naturally still has limitations. There does exist a frequentist alternative, the p-score. However, some authors have indicated that its interpretation can be a bit more challenging. While simple methods may be easier to understand, such as the probability best, they are often more unstable and don't encompass the entire analysis. The opposite is also true, i.e., whilst more complex methods are more rigorous, they can be harder to understand. And finally, interpreting ranking in isolation is not advised. There are many things to consider alongside ranking results, and not doing so can lead to exaggeration of results or misunderstanding. The literature also introduced us to lots of visualizations. There are too many to mention in this presentation, so I'll focus on those that I felt worked well and fitted within the remit of a single outcome, as this is what Meta-Insight currently works with. So first we have rankograms, which are a popular choice with lots of variations, and they essentially plot all ranking probabilities for all treatment rank combinations. They can present the results on the same or separate axes, can use lines or bars, and can present absolute or cumulative probabilities. Cumulative rankograms are also known as supraplots due to their direct relation to the sucra statistic by definition. Generally, rankograms were found to provide informative, balanced summaries of the distribution of ranks. However, some people have stated that comparing treatments can become difficult. An alternative that is less commonly used is a radial plot. Generally, radial plots have an outcome measure, for example, sucra, marked radially around a circle. Some variations use a donut shape and use color-coded sections to indicate the value. The benefits of this layout include the ability to present concentric circles to consider multiple outcomes or subgroups, and including other information nested in the middle, such as a network plot. However, a limitation of working on the radial scale is that generally humans struggle to discriminate between radii lengths. Next, the ability to display multiple elements of an analysis in the same space, a multifaceted display, allows researchers to present the larger picture. And this is great for treatment ranking, as it allows users to form robust and sensible inferences by drawing conclusions from a combination of sources. However, one does need to be careful to not overload the reader with large amounts of information. And finally, with advances in technology, a natural movement in the field of data viz is incorporating interactivity. Interactivity allows users to drill down further into the data or analysis as they wish, and can even involve users choosing their own settings. For example, this interactive visualization allows users to specify the relative importance of outcomes regarding treatment choices. So that was just a snippet of the literature that we found, and it provided great direction and knowledge when developing our own graphical tools for the treatment ranking within Meta-Insight. A few things to mention regarding how we developed these tools. Firstly, we decided to start with just Bayesian analyses due to its popularity in the treatment ranking field. Secondly, designing the tool was very much an iterative process of creating designs, sharing them, getting feedback, and going designing again, starting with pencil and paper and moving to mock-ups of different software. And the final designs were created in R, which is what Meta-Insight runs on, and the ggplot2 package. Now, before sharing what we came up with, let me quickly introduce the Exemplar Data Set for this presentation. This is the inbuilt example dataset in Meta-Insight for continuous outcomes, comparing pharmacological interventions for the treatment of obesity. And the outcome of interest is BMI loss 3 months from baseline, and the NMA was on 24 studies, including 5 treatments plus a placebo. So our first plot we're presenting, we've called the Litmus Rankogram. The base is a rankogram, which we chose due to its popularity and easy to understand nature. To aid interpretation, we decided to plot cumulative probabilities and to have all curves on the same axes. And with cumulative probabilities, one can then say that the nearer the curve to the top left corner, the better the treatment. It was reported that comparing curves can be difficult, so to further aid comparison, we added a litmus strip of sucra values, which has 2 functions. Firstly, to act as a key through the colours, and secondly, gives the sucra, which is easier to compare. So for this example, one can see that the ranking analysis indicates that rimonabant performs well, as we can see the green colouring, high sucra value, and probability curve being near the top left. For the converse reasons, placebo performed the worst. It's hard to discern between the 2 curves for metformin and orlistat subatramin, which may seem like a limitation. However, I believe it actually emphasises the point that they performed equally well. And next we have the Radial Supraplot. We decided to develop a second plot for 2 reasons. Firstly, as the number of treatments increase, a rankogram like before can easily become crowded. And secondly, we really liked the radial plot with the nested network plot that I showed earlier. And so we created this at the price of losing some of the granularity that the Litmus Rankogram gives. So for each treatment, its respective sucra value is plotted radially in descending order. We stuck with the sucra to not overload users with various statistics, and the sucra considers the entire ranking distribution whilst outputting a single value. To keep things consistent between the plots, the same color scale was used, with the colors of the nodes also indicating the sucra value. We are therefore aware that sucra is represented in two manners, and that could be seen as wasted ink. However, we believe it further aids communication and impact. So we took the plot by Ciara et al. And took it a step further by overlaying the network plot rather than nesting it. Therefore, the size of the nodes represent the number of participants in each treatment arm, and the thickness and presence of connecting lines indicate the number of trials that directly compare the respective treatments. And we felt that overlaying the network plot meant less work for the user and more impact. And the benefit of including the network plot in this way is easier to see if I unpack this example. So one can see that ribbon bound performed the best due to its high sucra and green color. However, it's actually quite hard to see ribbon bound due to its small node size from having a few participants in the treatment arms. Furthermore, one can see that it isn't very well connected to the network. These immediate factors should tell the reader that the result for ribbon bound should be interpreted with caution. On the other end of the scale, the large red node for placebo immediately shows that there is a good amount of evidence supporting that placebo did not perform well against the other treatments, and that we can be confident of that result. We noted that having the treatment network overlaid could become messy and hard to read for large amounts of treatments or connections. So in such cases, we've created a simplified version of the plot, which goes back to the original nested design. However, we've kept the nodes colored and sized according to their sucra and data. As I mentioned earlier, a key message that is present in the literature is that we should avoid presenting rankings in isolation. In this spirit, the final graphic ranking tool was designed to be a ranking panel. So here's the design. The central pane contains the ranking plots that I've presented, as these are the focus, the headline act. Then on the left, we present the relative treatment effects. This will aid interpretation of the ranking and reduce potential exaggeration, as an inherent risk of ranking is accidentally putting undue emphasis on treatments performing differently purely because they have different rankings. Then the aim of the right pane is to give users the opportunity to explore and interrogate the data behind the ranking analyses. Currently, this is just a network plot, but we have other plans that I'll mention later. Finally, I'm going to show a video illustrating how the ranking panel looks and performs within MetaInsight, our NMA app created with R and the Shiny package. Firstly, we run our Bayesian analysis and then click on tab 3C to access the ranking panel. And this is how the panel initially looks. The user can then switch between the two new ranking plots as they wish, including the simplified Radial Supraplot, and there is also an option to have the plot in a colorblind friendly color scale. All of the plots can be downloaded and the ranking results exported as a CSV file. Furthermore, as is the case throughout MetaInsight, there is functionality to run a sensitivity analysis where you can remove studies and compare the results. So this new treatment ranking panel is currently live in a beta version of MetaInsight, so please do have a look and play around. We do have future plans and ideas, including ones that I alluded to earlier in this talk. Firstly, there are plans to extend the contents of the left and right panes within the ranking panel. Regarding the left pane, we plan to allow the reader to switch between relative and absolute effects. With the right pane, we very much intend to increase the number of visualizations available to the user. Current plans include incorporating some form of risk of bias or grade visualization so users can see the quality of studies being analysed. And we also anticipate including David Philippo's bias interval plot, where users can ascertain what level of bias could change the results and thus how robust they are. We have lots of ideas for making the panel more interactive, including options to easily change the reference treatment where applicable. And we plan to look into using the Plotly package to enable further information via hovering. And unfortunately, it isn't just a simple thing to convert these ggplot objects to Plotly objects as they have multiple layers. And finally, we plan to wrap the newly developed plots into an R package so that other researchers can create them with their own data outside of MetaInsight. So thank you for your time today. I just want to acknowledge Will Stahl-Timmins, the Biostatistics Research Group at the University of Leicester, and the rest of the CRSU group for their input into developing these designs. And here is the link again to the app so you can explore it for yourself. Thank you.
Thank you very much, Clareece, for such an interesting presentation. And it's really great to see accessibility in the Meta Insight app as well. You're certainly giving Mark Lajournays a run for his money with your presentation skills this year. So Mark, you have a challenge to meet here ahead of your session tomorrow. So our final speaker in this session today is Taznim Hamza, who is a doctoral researcher at the University of Bern. Taznim, over to you.
Today, I'm going to talk to you about cross-NMA. It's a new R package to synthesize cross-design evidence and cross-format data using Bayesian network meta-analysis. So standard network meta-analysis synthesized aggregate data from randomized clinical trials because it is easily accessible from the published literature. However, heterogeneity may be present across these trials, and we include participant covariates or effect modifiers as aggregate information to explain some of this heterogeneity. Including mean covariates could, however, induce aggregation bias. So ideally, we would like to have or to include the covariates on the individual level from every study. But more typically, we only have IBD from a subset of studies and then aggregated data from the rest. In terms of study design, most NMAs include only clinical trials in the analysis because they are typically at a lower risk of bias. But on the other hand, they are conducted for a restricted set of population, and this makes their results hard to be generalized to the general population. On the other hand, the non-randomized studies or observational studies reflects better the reality, but it comes with high risk of bias. We might need in some situation though to combine these types of evidence while taking into account the biases on each design. And this is what the cross-NMA model is doing. It's a recent extension of the NMA model to synthesize mixture of data formats, IBD and aggregate data, and different study designs. We built the cross-NMA model by integrating these 4 different approaches, which combine clinical and observational data into the 3-level hierarchical model that synthesize IBD and aggregate data. How does the 3-level hierarchical model work? First of all, we define an individual level regression model to include participant covariates. Here, beta 0 captures the prognostic effect. Beta W is the within study treatment covariate interaction, and beta B quantifies the interaction between the relative treatment effect and the mean covariate value on study level. And then for aggregate studies, we have access only to mean covariates, so we can only estimate the coefficient beta B. Then we combine the evidence across IBD and AD for relative treatment effect, delta and covariate coefficient beta B, while beta W is combined only from IBD studies. Now, how do we integrate the 4 approaches to combine clinical and observational data into this 3-level hierarchical model? So the simplest approach is to not differentiate between the 2 types and fit individual regression model for both clinical and observational studies, and do the same for the aggregate studies. But we know that each type has different level of bias, and this model doesn't account for this bias. And this brings me to our second model, which adjusts the relative treatment effects to the bias on each study. For individual model and aggregate model, we add this highlighted part, the bias effect of each study, gamma multiplied by the bias indicator of that study R. The bias indicator R takes values 0 or 1 based on the assessment using the risk of bias tools. However, we know that the judgment using these tools is subjective and carry many uncertainty and carry many uncertainty, and we reflect this uncertainty by assigning a Bernoulli distribution to the bias indicator, which will provide 0 or 1 to R. But now, and to estimate the probability of bias on each study, we either assign a beta distribution. Low risk of bias studies are given distribution skewed towards 0, and high risk of bias studies skewed toward 1. Or we could estimate the bias probability using study characteristics through this logistic model. There is another way to reflect study bias by directly modeling the bias-adjusted relative treatment effects theta, which is estimated by a weighted average of unadjusted effect delta and the bias-adjusted effect delta plus gamma. In bias adjustment model 1, in the slide before, this theta is either the unadjusted effect for low risk of bias studies or is a bias-adjusted effect for high bias studies, and not both of them. But here we allow theta to be weighted average of both parts. But for low risk of bias studies, we give a greater weight to unadjusted and a little weight to bias-adjusted part, and vice versa for studies at high risk of bias. The last approach in combining clinical and observational data is using observational information as a prior to model the clinical evidence. It is a two-step approach. First step is to conduct network meta-analysis only for observational data using individual aggregated data or mixture of both. In Bayesian framework, we will get a posterior distribution of each relative treatment effect. Second step is to conduct network meta-analysis for clinical data, but as a priors, we use the posteriors we get from the observational data. Now, some people could argue that usually observational data has a greater sample size compared to clinical trials, and this makes the observational information dominate the estimate. So to control this potential high influence of observational studies, we downweight the contribution from these studies by increasing the variance from the posteriors here, or make these distributions further. These models are implemented in the crossnma package, which is a suite of tools for performing network meta-analysis and meta-regression with individual participant data, aggregate data, or mixes of both. And each format can come from clinical trials or observational studies or mix of both. Behind the scenes, models are estimated in a Bayesian framework using JAX in R. The package allows for conducting standard network meta-analysis when we have aggregate data from RCTs. It allows the inclusion of IBD of these RCTs, and it also enables each format to include observational studies. So a workflow in crossnma model is as follows. First of all, you start with your data sets, participant data, and aggregate data, or only a single data of one of them. There should be both of them in a long format, which means one row per arm, per aggregate study, or per participant in IBD. We then call the crossnma model function to construct a JAX model and reformat the data. We might visualize the network, and then we run the analysis using the crossnma.run function. And once the model is fitted, we then can produce summary of results, league table, or check the convergence. So let's apply this to an example. First of all, we have some individual participant data at the top here. So one row per each individual. And you can see that we have, in this example, a binary outcome. And then we have aggregate data below this, one row per each arm study with their outcome and covariates. On each data set, you need to have at least these highlighted columns: study ID, outcome, the assigned treatment, and the design of the study, clinical or observational. And for aggregate data, you need additionally to provide the sample size column N. Combining these together in a cross-NMA model, first of all, you need to indicate the name of your individual participant data and aggregate data. You need then to indicate columns name of these variables. And you then choose which model to be used to combine treatment effects across studies, either random or common effects model. You set the reference treatment. In this example, relative treatment effects will be evaluated versus A. And finally, you indicate which approach you would use to combine observational and clinical data. Here goes one of these 4 approaches that I talked about before. To conduct network meta-analysis, meta-regression, you could set a covariate. Here we use age to adjust all relative treatment effects. And also you could adjust the relative treatment effects to study bias using bias adjustment model 1. And here there are too many arguments to be set as well. All will be described in the help file and the vignette. You can also plot the network using the netplot function. You could pass to this function different arguments to control the colors, the thickness, and many other features, which are very similar to the netgraph function from NetMeta package. And then you can go away and fit the model using the crossnma.run function. It takes the model we created using the crossnma.model, and you need to set the settings for MCMC samples, iteration, burn-in, and etc. Once we fitted the model, I can then print a summary of the results. So here it's showing us the mean, standard deviation, etc. for each of the parameters. We have here the regression parameter P, the relative treatment effects D, and the bias effect, plus the 2 heterogeneity parameters. Also, to provide the convergence information, the Gell-Mann-Robin statistic, and the number of effective sample size. You could also produce the trace plot to check convergence of each parameter. And finally, you can create the leak table by crossnma.leak function. So here the values in each cell shows the relative treatment effects and the 95% credible interval of each treatment on top compared to the treatment on the left. So I really just gave a brief summary today. If you would like to find out more, and you can check out our package on GitHub website. Soon we will submit this package to CRAN with the Illustrator documentation and detailed example. We also soon submit our methods paper. Thank you very much.
Thank you very much, Tasnim, for your excellent presentation on cross-NMA and how it can be used with both individual participant data or aggregate data. And I'm really looking forward to that paper and its arrival on CRAN. So that's it for this session on NMA. We hope you enjoyed it as much as we did. And thanks so much to all our presenters. We'll see you at the next session, which kicks off with multiverse meta-analysis, and we'll start in just over 30 minutes from now. Thank you.